Good morning, my fabulous chemistry students. Unit 9, Acids and Bases. Today we will do video 1 and we will look into the characteristics of acids and bases. When we are done with this video, you should be able to identify some of the physical and chemical characteristics of acids and bases and understand what kind of ions they produce in solution. And here we go, back to solutions. And we just did this unit 2 units ago, right? Going to keep coming into play. We know that acids and bases exist. What are their characteristics? Acids and bases are a specific class of chemical that react uniquely when I put them into water. They are going to deionize very much like an ionic solid would. Okay, so let's start with acids. Table K in our reference table is going to give us a list of the common acids and bases. These are the ones that they're probably going to talk about on that big bad test, and we're not going to learn all of them because there's lots of them. I want you to take notice, though. Notice that they all kind of seem to start with this H, except for when I get down here. This is the exception. We call it a Cu. It is an organic acid. Okay? So they all start with H except for that one. That's just a little heads up into some of the notes we're going to do later. Dilute acids have a very sour taste, and these you've actually eaten before if you've ever had lemon juice. Citric acid vinegar on your salad is acetic acid. All right, there's carbonic acid in your soda. And this is true if you ever find any of the baby teeth that mom's got stashed around from when the tooth fairy took your teeth. If you find one of those teeth and you put it in a glass of Coca-Cola and you come back in a week, that tooth will be completely gone because that acid will eat it. Concentrated acids will burn you and eat holes in your clothing. You will not find many concentrated acids on the open market except for in chemistry class with Mr. Milks or Monaco. Aqueous solutions, when I put an acid into water, I form an electrolyte. An electrolyte is something that produces electricity. And we'll find this very common in our car batteries. They have a very strong acid. So the greater the concentration, the more ions, so the more I conduct. Weak acids then will be very poor conductors. Strong acids will be very good conductors because the more ions I have in solution, the more flow of electrons I can create. Acids will react with bases to form neutral solutions. You can think of acids and bases as opposites. Okay? They will form a double replacement reaction. That's one of the 4 that we learned earlier. It has a specific name called a neutralization reaction. And this is what it looks like. If I take an acid and a base, and I put them together, I will always form a generic salt and water. So we have an example, and let's go through it quick. Double replacement reaction. So I'm going to take the positive ion H and hook it with the negative ion hydroxide. I'm going to take my negative ion from the first species, Cl, and hook it with my positive ion Na. Okay, and just so we know that this is the acid over here, and this is the base. We haven't done a lot about bases yet, but we did see that acids start with H. So I'm going to come up with 2 new species. I have an H with an OH. That's HOH. Does that look kind of familiar? I bet I could rearrange these around. I have 2 H's and an O, so I could write H2O. Ah, that looks a lot more familiar. And I have Cl and Na. And we know when we do these, I'd never write Cl first and then Na because Cl is negative and Na is positive. We have to write the Na first. Okay, there we go. NaCl, I have a salt and water. Make this look neater, I'm going to rewrite this as the water that we so commonly know. And a quick balance, I see 1 H and 2 H's. No, I see this other H here, so we're good. 1 and 1 and 1, 1, we're good. That was a quick, easy one. Acids react with certain metals to produce hydrogen gas. Boom! Single replacement reaction this time instead of a double. We keep track of them on table J, which we will get to in the last notes of the unit. We will look into table J more closely. If I take my acid, my positive ion is going to not have a negative ion to hook up with because this is a single replacement reaction, right? And then my negative ion has a positive to hook up with, so I'm going to make NaCl. And I'm going to make hydrogen gas by itself. And this is where learning those diatomics comes into play, because H never exists by itself. It's always H2. And now I have to balance because of that. So I have two H's, now I have two H's, I have two Cl's, so I need two Cl's. Then I made two NA's, so I've got two NA's, and now I'm balanced. Now I made 2 moles of salt and hydrogen gas in my single replacement reaction that acids do with metals. Acids and bases, we have indicators that just tell us about strength, and an indicator is something that basically just changes colors. We did this in living environment some. Phenolphthalein, I believe we used. No, bromothymol blue was a big one in living environment, if I remember correctly. Phenolphthalein is what we'll use in our titration lab towards the end of the unit. All right, so basically, the change in color helps me decide where I am in the pH range. And there's a whole list of these indicators, and there'll be actually a whole video on just indicators so we can get close, delve a little deeper. Acids have pH values less than 7. Less than 7, they're low on the pH scale. This chart helps us see this, and this used to actually be in the reference tables. So here's my 7. This is neutral. Everything below 7 is acidic. And this is how we read it. Not only are the H's bigger on the left than they are on the right, but notice this here is 100% H plus ion. This here is, let's say, 66%. And right here at 7, we are half and half. So it's 40 or 50-50. So this is how I see that the bulk of the solution is H plus ion. The more H plus ion, the more acidic I will be. We will learn that it's a logarithmic scale, which is one of my least favorite math pieces. General formula, HA or HX, where this X is a negative ion, such as chlorine. Okay, and notice there's an H. Hydrogen with a negative is our general formula for acids until we delve deeper into acid-base theory in a few notes from now. Bases. Changing gears. Now let's go to the opposite. Acid started with H. Nothing here in this list starts with H. Oh, and look, they gave it its own little table L. You're going to find this is right under the common acids table in the reference table. And if we look at these real carefully, they all tend to end in OH, and there's one exception, NH3. We will delve deeper into the exceptions later. Dilute bases have a bitter taste. Antacids, soaps, ammonia-based cleaning products, I hope that none of you are tasting these things, but what we will find is that they're very slippery or have a soapy feel to them. If you ever got a little bit of bleach on your fingers and you rubbed your fingers together, it's almost like slimy, like they slide over each other. That's a base. Concentrated bases will burn your skin and eat holes in your clothing. So, something like lye will really, really burn you really bad, and you don't want to be getting any of that on you. Aqueous solutions are, again, electrolytes. They form ions that produce electricity. The greater the ions, the more conductive. Okay. Their weak bases are poor conductors, and strong bases are good conductors. Bases will react with acids to form neutral solutions. So this is that double replacement reaction again. Same generic equation, acids plus bases are going to give me a salt and water, and I have a different equation to do. So I'm going to, again, take, this is my acid with my H, take my plus ion, add it to my negative ion, and then from the acid, the negative ion is going to hook with the positive ion from the base. And I'm going to form HOH, we learned before, is H2O, so I'm going to jump right to that. And then I have bromine and calcium. I'm going to write calcium first because it's positive, CaBr. And here's some old rules we have. Remember, the charge on calcium is a +2, so that 2 is going to cross down to be Br2. And the Br is a -1, so that crosses down to a 1 on the calcium. I don't need to write that. And this is where I now get to balance. I have 2 BRs on the right. I need 2 on the left. I now have 2 H's, and it looks like 2 H's, but I don't have just 2 H's. See, I have 4 total. So I need a 2 here to give me 4 total H's. Now I have 2 O's. I have 2 O's. I have 1 Ca. I have 1 Ca. We're good. Bases cause acid-base indicators also to change color. We use litmus paper and phenolphthalein for this. Bases we will find have a higher pH or greater than 7. So this is on this side. In between 7 and 14, I am now basic. And again, look, the percentage of solution is higher with OH here. And even here, more OH than H. And then right in the middle, 50%. Half and half is neutral. Okay, so the general formula when I write that is XOH, where X is any positive ion called an anion, such as sodium. Now, we can identify characteristics of acids and bases based on how they dissociate, that they're electrolytes, some of their physical properties like taste and feel, even though some of them we're definitely not going to taste. You can go ahead and do practice page 1 now, and there is no CASEL assignment for this particular lesson. I'll see you guys in school tomorrow.